So hello and welcome to AI for Predictive Maintenance seminar series. I am Madhav Misra and I am hosting this seminar series. RISE organized monthly seminar on this topic for AI for Predictive Maintenance. So please feel free to spread this word to anyone if you think they are interested. Today we have a speaker from DLR, German Aerospace Center, Mr. Robert Meissner, and he will present on the topic of beyond prognostics, prescriptive maintenance strategy in the aviation industry. Robert is a researcher at DLR Institute for Maintenance, Repair and Overhauls in Hamburg, Germany. His research focuses on advanced maintenance concept and prescriptive maintenance in particular. His research aimed to develop innovative physics-informed AI models that improve the accuracy while reduce the AI carbon emission. The presentation will last approximately 30 to 45 minutes, followed by the question and answer session. As always, this seminar will be recorded and shared with the audience and upload on our YouTube channels for those who miss it. I hope this is okay, Robert, as I already asked your permission.
Yeah.
So we are so glad to have you with us today, Robert, and welcome, Robert. The floor is yours. Please start sharing your slides, and we are interested to hear your work. Thanks.
Yes. Hang on a second. I first need to figure out how to share my presentation. Here. So just give me a quick thumbs up. Does it work? Yeah, perfect. Okay, so yeah, welcome also from my side. As mentioned, my name is Robert Meissner. Thanks again for the opportunity to present here in front of the audience and your institution. Yeah, today we will cover the topic of prescriptive maintenance, and I try to come up with a rather catchy name, so I named it Beyond Prognostics, Prescriptive Maintenance Strategies in the Aviation Industry. I thought about the following agenda for the next 35 to 40 minutes. First of all, yeah, well, now you had the introduction of myself already, but I will cover more like what we do as an institute, where we come from, where we are located, and what our research topics are. Then I'm trying to give you some motivational background information. So why should you even be bothered to think about post-prognostic maintenance? What do we see as current challenges and obstacles in the development of prescriptive maintenance strategies, and what do we even mean by prescriptive maintenance? And ultimately, I would like to conclude my presentation with some use case scenarios that we have calculated, that we have simulated, and trying to get the message across what benefits prescriptive maintenance can deliver to your organization and where it can help. Maybe just some additional information about my side. I've been with DLR now for about 5 years. And I'm a graduate from TU Berlin with a master's degree in engineering and management and a bachelor's degree in transport system. Everything else has been mentioned already. So quick overview of our institute. We are located in Hamburg, Germany, so here in the northern part, symbolized by this green dot. And we have been founded in 2017. So basically we're almost 5 years now, 6 years now. And we are located at the ZAL, which is the German abbreviation for Center of Applied Aeronautical Research. We are located in Hamburg-Finkenwerder, in close proximity to Airbus. And as of today, we are about 40 employees, but we are constantly growing. So this number is expected to increase throughout this year as well. Down on the slide, you can see an idea about the research topics that we are covering currently. And this should just give you a brief introduction of what we are doing. I mean, we are quite a diverse group of researchers that are working here. So there's a lot of research going on, but it starts with MRO concepts and decision support. This is where I mainly am located. And this covers all the maintenance aspects for upcoming aircraft ideas or aircraft concepts, but also covers topics of how would maintenance change for retrofits within legacy aircrafts. Then in our institute, we are also doing a lot of life cycle cost benefit analysis, but more recently we are shifting also our focus more towards sustainability integrated analysis. So not just focusing on monetary values, but also on sustainable aspects. Then a big part in our institute is the human-machine interaction. So how does the human-focused MRO technology, how could an ideal MRO technology look like? And yeah, what do we understand as robot-assisted repair systems and how do they work? And yeah, the main pillar in our institute is everything about digitalization, starting from MRO process analysis, trying to identify how can processes be improved in the future, what are areas of improvement, and also the big point of data analytics and predictions. So this just as a quick background information for our institute. And for this presentation, I thought about, okay, let's give it a catchy hypothesis that we are working along. And what I would like to examine with this presentation is that there's so much development in the industry going on right now to develop continuous condition monitoring technologies. However, what I state here is that if we don't adapt the maintenance strategies accordingly, all the developed continuous condition monitoring technologies will yield only limited benefits, if any benefit at all, whenever they are introduced. And what are we trying to do? We of course, we propose some adaptation for the maintenance strategies in order to yield some higher benefits, whatever that means, an order of magnitudes. All the numbers you see here in the next 4 slides, they don't originate from me, so from other experts. I hope they get some credibility therefore as well. And all the numbers I'm showing here are from studies that have been conducted before the coronavirus pandemic. So the numbers might look different right now as time has passed, and the world of traveling and the world of aviation looks certainly a bit different than it looked back in the days. But yeah, the magnitude of the number should still apply and should still hold true. In one of the IATA maintenance cost conferences in 2019, they stated they estimate cost saving potential in the aviation MRO industry of about 3 billion euros. And this comes mainly through the usage of digitalization technologies and the subsequent avoidance of operational interruptions. And this insight also does not singularly apply to the aviation industry, but also applies to different industries. For example, PricewaterhouseCoopers conducted a study among 200-ish manufacturing companies in Germany, the Netherlands, and Belgium. And the topic of this study was Industry 4.0, so basically the same idea than predictive maintenance, with some other side aspects as well, but we're focusing on the predictive maintenance part in the study here as of the numbers. And the majority of the companies said they are expecting, through the utilization of post-prognostic maintenance approaches, they are expecting an improvement of the operational uptime of their machines. However, in the same study, just a fraction of the company was even capable of enabling a continuous condition monitoring of the systems they are running, the machines they are running. And back in the study in 2018, it was 11%. Nowadays, it might be a bit higher. But given that it is such an essential requirement to have a continuous condition monitoring, to even talk about and think about implementing post-prognostic maintenance approaches, this value is way too low and way too less capability is existing there. And this also leads to the conclusion of the study that almost 2/3 of the companies struggle to identify viable business case scenarios, which is quite frankly, I mean, it is obvious when you're struggling with the most basic technological needs of the continuous condition monitoring, then you also will struggle to identify return on investment whenever you have a new technology applied in there. And this leads ultimately to, if you can't determine what return on investment you have, then you are less likely to invest further in any technological improvement, which delays any viable business case scenarios even further. So this is some sort of negative development cycle that we are trying we try to stop, or at least play our part in stopping this negative development cycle. Before we go into detail about prescriptive maintenance, I just want to make sure that we're all on the same level and understand the same as maintenance strategies. So in this slide, I will just briefly cover the different classifications of current aircraft maintenance standards. And I'm trying to rank them from simple approaches to more complex approaches, and also from purely reactive to proactive approach. And by reactive, I mean you perform a maintenance task after a failure has occurred. Proactive is defined by you're trying to prevent the failure occurrence by proactively planning what maintenance needs to be done before. And arguably the simplest and the most, by its very definition, the most reactive maintenance category is the corrective maintenance. And if you want to put a slogan on it, it might be, if it ain't broken, don't fix it. So corrective maintenance is characterized by operating a system as long as it lasts and as long as it's working, without doing any functional checks or premature replacement in between. And you will just react once a system failure has occurred. As at least in the aviation industry, that doesn't really apply to safety critical systems. And therefore, in the aviation industry, people had to come up with different solutions. And one of the solutions they came up was the predetermined maintenance. However, it has to be noted that the peak of the usage of predetermined maintenance has been, well, maybe in the 1960s, 1970s, with former maintenance approaches. And the basic idea was to replace items in fixed time intervals. You wouldn't check for any condition, and you wouldn't wait until a system fails, but based on expertise, on operational experience, on manufacturing recommendations, you replace items in certain intervals, regardless of the current state of degradation. The current state of art, at least in the aviation industry, arguably is the condition-based maintenance approach. And there you constantly monitor the condition, and you react on the reading that you have observed through one of the condition monitoring tasks, and trying to do some suitable maintenance tasks. This can become rather complex because still up to the point where you conduct your condition-based maintenance, so basically where you monitor your condition of the system, you don't know what the system condition will look like and what subsequent maintenance needs will arise. So therefore, you need to have sufficient manpower to perform any subsequent replacement or repair tasks, and you need to have the suitable inventory available for quick replacement to get the aircraft up and running as fast as possible. If you're trying to extend this current insight of my state of degradation into the future, and you're trying to also to project the condition into the future, and also obviously trying to plan my maintenance tasks accordingly, then we're talking about predictive or even prescriptive maintenance. As any projection into the future, and some of the audience certainly will know because they are dealing with that in their professional life, know with any prediction there comes a lot of uncertainties associated with it, which makes it rather complex already from the task of the prediction. And when we're talking about prescriptive maintenance, then we're trying to extend our scope beyond the asset itself. So there will not just be uncertainties for the prediction, but also uncertainties associated with the involved stakeholders for the maintenance planning. What it means specifically, we will come back to that later. However, a huge advantage of predictive maintenance is that it's arguably very proactive. As you, in an ideal world, you can prevent any failure before it is actually occurring. So now I have mentioned proactive maintenance a couple of times already. I just want to make sure that there's no such singular thing as proactive maintenance. So there are various shades of gray, if you will, and the simplest, quote unquote, the simplest proactive maintenance is descriptive maintenance. And these are basically best practices. So you're looking into your past history of maintenance activities, You see what error message an aircraft has given you, and what maintenance task subsequently has been performed. And you can also examine what the efficiency of this maintenance task has been. So this is a pure retrospective analysis. If you want to gain some insights in my current state of degradation, then we are within the field of diagnostic maintenance. There you need to have some idea about failure mechanism and degradation mechanisms in my system. And if I want to project that into the future, then arguably we are at one of the most discussed maintenance strategies, which is predictive maintenance. And predictive maintenance is characterized by giving remaining useful lifetime. So basically between now and my ultimate system failure, I have a specific time frame. But predictive maintenance just gives me an end date and a starting date. So starting date is today, end date is when the system is going to fail. However, predictive maintenance does not prescribe any actions in between. So which maintenance opportunity up to my ultimate system failure should be chosen in order to optimize whatever my target or my objectives were. And this is where prescriptive maintenance comes into play. As I mentioned earlier, it tries to extend the scope beyond the asset itself and also incorporates the associated stakeholders to exactly identify which maintenance opportunity to choose from in order to perform some maintenance. So what are current challenges that we, at least from a research perspective, have identified, but from discussion with industry, we see, okay, some of them apply also to industry, at least to industry that we have talked to. And first of all, a lot of the solutions that exist, and there's quite a variety already existing, is characterized by a strong asset centricity, which makes sense for the provider of this solution, as they want to, for example, an aircraft engine manufacturer wants to make sure that the engine is up and running as much as possible. So the manufacturer or the service provider for this engine trend monitoring technology is focusing solely on the engine. However, the core idea of prescriptive maintenance and to be even able to identify the maintenance opportunity, it is insufficient to just look on one singular asset, but you need to extend the scope beyond the asset itself. And this brings us directly to the second point. We have, at least in the airline MRO, aircraft MRO industry, we have a lot of stakeholders that are interlinked with one another, and they have different objectives, and sometimes these objectives are competing with one another. So you need to be, first of all, you need to be aware of what stakeholders are even essential for your maintenance decision to gain any benefit. And you also need to be aware what are the interactions between the stakeholders with regard to their individual objectives. Then when we're talking about PHM technologies, and just to be sure, PHM stands for Prognostic and Health Management. So basically these are the condition monitoring and condition projection technologies that are installed on the aircraft. And a lot of these systems have a rather low technological maturity. Most of the system, or a significant portion of the systems and the algorithms, have been developed in laboratory conditions, so under controlled environment. And as I mentioned earlier, when we're going in a real life scenario, we have uncertainties with respect to the operating condition. For example, if the system's degradation is subject to some environmental adversity, and I need to project the next 2 months of degradation, then I also need to know what the environmental condition in 2 months will be, which of course inherently is associated with some uncertainties. And also we're talking about aircraft designs that have been developed back in the 1980s, 1990s, where the primary focus was not to equip a system with so many sensors, for example, to even allow any continuous automated condition monitoring, let alone any projections. So this is an issue we are dealing with. We have different maturity levels, and this also needs to be reflected in the maintenance decision making then ultimately. And last but not least, at least in Europe, we see the discussion in society and also in government that it is not just sufficient to look on monetary values as well. A lot of the focus right now is shifting towards more sustainable solutions. So while it is perfectly fine and it is essential for a service provider to, in order to be self-sufficient, the system and the solution needs to make some money and needs to provide a viable business case scenario. A monetary objective is insufficient to be viewed individually, but needs to be combined with some sustainable aspects, such as a reduction in energy consumption, for example, for the maintenance task execution, or also material requirements. If you're looking into how are post-prognostic maintenance tasks derived, I thought about a cycle, how I could prototypically depict it here. And given this cycle is idealistic and even very simplistic, but just stay with me here. It is important to note that we have three different aspects, basically. So first, we have the business case identification, then we have the technical implementation of our pure condition monitoring techniques, and then we have the subsequent maintenance action. And if we look at the cycle, without going into too much detail, we can see that industry and also research is very strong on the areas that are marked green down here. So basically the technical aspects. We have gotten better and better in reliability modeling and predictive algorithm design and understanding what my performance of the system currently is and how it can be monitored. And we're also getting better in the failure prediction or in early fault diagnosis. However, we are lacking significantly in the subsequent task prescription. So what are we going to do with the information? This is what we are covering right here. But also, at least what we have seen from discussion with different industry partners, it is not always clear what performance a PHM technology needs to be delivered in order to be deemed successful or be even suitable to be applied in a real-world scenario. So, for example, if my current maintenance approach says, okay, I'm doing my regular condition monitoring and functionality checks, where a mechanic is going there and visually inspecting some system, and now I want to apply a PHM technology there. There's no set and no given standards, at least oftentimes. Okay, the PHM performance, the PHM system needs to perform at least with a prognostic horizon of X flight cycles, with an accuracy of whatever percentage, and can have a false positive rate of maximum this percentage. And this makes it really hard then to also estimate, okay, what will the return of the investment for this specific technology be? And is it even worth to be installed and be applied in a real world scenario? And this is exactly what we are trying to address here in our institute. So now, with all this background, I thought about giving you a short definition, if you will, that we are following here in our institute of prescriptive maintenance. And for us, prescriptive maintenance is a development of predictive maintenance. So basically, it utilizes a system failure projection. This is exactly what I mean. What I meant earlier when I said I need to have a remaining useful lifetime in order to have a set of maintenance opportunities to even choose from. So this is my prerequisite in order to be capable of prescriptive maintenance. Then I'm trying with prescriptive maintenance, I'm trying to minimize adversarial implications for the involved stakeholders. I try to reflect with the wording a bit that we are not just focusing on monetary values, but there's a whole set of values which ultimately, of course, can be transferred to monetary values. However, it is not very helpful if I transfer a CO2 emission, for example, directly in a dollar value, just to have a comparability for dollar values. What exactly that means, I will show you in one of the use cases. And then the highlighted word of involved stakeholders, that is the emphasis. Okay, we need to have some sort of holistic analysis. So basically, we need to extend our scope beyond the asset itself, and we need to be respectful, if you will, towards the individual objectives of the involved stakeholders. What are we doing here with that regard in our institute? We are developing a Python-based discrete event simulation, and this discrete event simulation is called PREMATE, which stands for Prescriptive Maintenance Developer. And PREMATE has exactly the idea of representing the key players of our MRO ecosystem, setting them into interrelation with one another, and also be capable of applying different PHM technologies in order, ultimately to see what the results and towards the objective for the individual stakeholder will be. I mentioned stakeholder a couple of times. Next slide, I will actually show you what I mean by that. It is very important to note, at least for us in the current state, we are not trying to come up with a globally optimized maintenance solution and saying, okay, this maintenance opportunity is the very best under any circumstances. First of all, we try to understand what the interactions among the various stakeholders are with respect to different technological maturity levels of the PHM system. So we are trying to address, okay, if we apply a prognostic system for a specific aircraft system, let's say the landing gear, then we will have the following effect on the MRO provider. We will have the following effect on the operator, and they are in a relationship with one another. And this is what we are trying to assess here. Then we are a research institution, which is important to keep in mind, as we don't have all the data available as Airbus, for example, has, or Lufthansa here in Germany with Lufthansa Technik. So basically, we need to come up with our own, let's say, data lake. And this is the strong suit of the discrete event simulation. So basically, our discrete event simulation will log every single simulated event that is happening and write it down diary. It looks like a diary. So basically, a component has been replaced. The replacement took so and so long and was so and so expensive. And we can take all this information down, and this discrete event simulation approach then ultimately enables us to have some flexibility of our analysis metrics. So basically, we can decide afterwards, after we have run the simulation, we can decide, okay, what will be the focus of our analysis be? And this is the huge advantage of the discrete event simulation over, for example, a set of mathematical equations. There are some in research existing. They have been developed a couple of years ago already. However, they have a single PHM technology and a single objectives in mind. So basically, if I change my objective or if I change the stakeholder that I want to examine, I need to come up with a new set of equations. I need to start all over again. And with our discrete event simulation, we can very easily tweak the input results and subsequently have a new set of output, of simulated output data that we can then ultimately analyze to see, okay, what the interactions among the various stakeholders were, and what for example, the cost benefit analysis would yield then. So now, as promised, the stakeholder model. So this is the key ingredient actually of our tool, of the prescriptive maintenance developer. And you can see here, don't get confused that it says model here. So basically this translates to the logistic provider in real life. So we have three different stakeholders that are interacting with each other. This is the operator. This is the maintenance provider, and in aviation at least, the maintenance provider can be subdivided in a line maintenance and in a shop maintenance part. The line maintenance basically means everything that is happening to an aircraft at a designated maintenance hub, and shop maintenance is every maintenance task that is happening to a part once the part has been removed from the aircraft and sent to a designated repair shop facility. And then we have the third stakeholder, which is the logistic provider. And first of all, what you can see here, all of them are constantly interacting with one another. They are exchanging information in order to derive subsequent actions for themselves, but also to enable PREMATE to come up with a maintenance decision. And the operator, as the name implies, the operator is responsible for operating the aircraft. So it performs the flight, it checks for any curfew restrictions, and whenever the aircraft is delayed, the operator is also responsible to pay some passenger compensation if applicable. Then we have the maintenance provider, and the maintenance provider basically is responsible to provide maintenance resources, and these could be skilled mechanics or ground support equipment. And the line maintenance provider, as mentioned earlier, performs everything on wing, and the shop maintenance provider performs everything off wing. And last but not least, the logistic provider supplies the maintenance provider with needed spare parts. So the logistic provider is responsible to keep track of the current inventory, make sure all the inventories remains in an airworthiness condition, and supply the required amount of spare parts needed in a timely fashion. Then we also have this box. This is not a stakeholder, but this is essential for our software solution. Here we have the degradation model. We had to go to a very basic degradation model here in order to have some flexibility also for the scope of the analysis. Going back, mentioning earlier what I mentioned earlier, we are a research institution, so basically we don't have all the data and can come up with degradation model for all systems that are installed currently in an aircraft. So we need to boil them down to a very simplistic degradation model. But this is only responsible to have some degradation even happening in order to issue any maintenance tasks and have even the need for maintenance tasks coming up. So there's no limitation, at least from the simulation perspective, in this rather simplistic degradation model. I don't want to go any further into detail right now, so maybe just one more information. All these boxes, all these stakeholders are translated in our Python environment into actual classes. So basically every instance is there, every stakeholder is there an instance entity that has a set of functions and attributes associated with this, and exactly as shown here in a graphical way, exchange information in order to come up with maintenance solutions. So I would say enough about the theoretical background. So I want to give you some exemplary scenarios about use cases that we have examined so far, where we had some, I hope, some interesting insights. At least for us, they were interesting. And but before we go into the scenarios, just a bit of setting the scene, so you get an idea of what we actually examined here. We did analyze an aircraft fleet that consists of Airbus A320, so it's a short and medium haul aircraft that is operating in a hub and spoke scenario that is located in Munich, and the flight schedule is similar to one of a major German airline, and everybody who has been to Munich probably knows which major German airline that could be. Then we also have for the maintenance provider, we have simulated a limited availability of our ground resources, and by ground resources in this instance, we mean available qualified mechanics, and also we allow maintenance tasks only to happen on our main hub, Munich. So basically, we also have a limitation of our suitable maintenance hubs where our maintenance tasks can be performed. As of this presentation, there has been no limitation with regard for a spare part supply. We are working on it right now. As of this presentation, there was nothing to present on this instance, so I skipped that. But we will hopefully soon have some analysis how post-prognostic maintenance has an effect on the spare part supply. And whenever this publication is out, we will also post it on our LinkedIn channel. So have a look there and check our updates. And last but not least, the system that we have examined is the aircraft tire pressure maintenance task. This has two basic advantages. The first advantage is it is, from a technical standpoint, it is rather simple to simulate. So basically, there's only one degradation mechanism, and this is the loss of tire pressure. And the second part is it is happening extremely frequent. Every third day of operations, an aircraft operator is required to have a mechanic physically going to the aircraft with a pressure gauge and checking the aircraft tire pressure. and identifying if the aircraft tire pressure applies and is still within the limits of the manufacturer, or if any subsequent maintenance task is necessary. And also we have extended preparatory times for cooling. So whenever an aircraft has landed, the manufacturer requires the tire to cool down for about 3 hours, 2 to 3 hours it was, I guess, in order to cool down to ambient temperatures, so I don't get any temperature-induced pressure inaccuracies in my pressure reading. So with this setting the scene, the first question that we have examined is, I mentioned it earlier, that we are dealing with rather immature, at least from a technical perspective, rather immature technologies. And we try to identify, okay, how does the technological maturity affect my improvement of my airline operations, and how does the technological improvement change my airline operations? Is there some sort of pattern visible there? And first of all, what the basic idea behind there was, let's just assume, let's go to the top part of this figure here. Let's just assume we're having 2 aircraft, and both aircraft are following their flight routine, outbound from Munich, inbound to Munich. And as it's, by coincidence, both aircraft will have a maintenance need at the same time instance. And I have a limited ground resource availability, so basically I can only serve 1 aircraft at a time. So rather straightforward. Whenever this aircraft will be served, the second aircraft needs to wait for their service, and the maintenance will then be delayed, so that the aircraft, the subsequent operations will be delayed, even here in this extreme scenario, into curfew hours at my home base, and every subsequent flights will be delayed or need to even be cancelled. The prescriptive maintenance scheduling is rather straightforward. So basically, I'm just trying to relax this competing scenario here for the ground resources by moving maintenance tasks to earlier time points. So therefore, artificially decreasing my remaining useful lifetime for 1 aircraft, and therefore I don't have these competing this competition for the limited ground resource. And both aircrafts can be served without any subsequent delays. And what it looked like in the results. So here on the x-axis you have the prognostic horizon. We increased the prognostic horizon from 0 flight cycles up to 18 flight cycles, and this is our understanding, or at least it symbolizes here in this analysis the technological maturity of our PHM system. And on the y-axis there is the average total waiting time of our fleet. Then we also changed and we altered the maintenance operating window. So basically we started with a 24-hour operating window, and we continuously decreased that down to an 8-hour maintenance operating window per day. And what we can see, basically there are 2 key observations. The first is, and this is not really surprising, my operational implications, so basically my delays, will decrease with an increased technological maturity of my PHM technology. So basically, whenever I increase my prognostic horizon, my operational implications will be reduced, and I won't have this many delays. However, there's a second important observation. There are saturation points, and it doesn't really matter that at this chosen numerical example that we have examined here, it is 8 flight cycles. The number doesn't matter, but there is a saturation point where whenever I have a PHM technology that is worse than this saturation point, so for example, I have a prognostic horizon of just 4 flight cycles, look ahead time, then any increase or any additional improvement of my PHM technology will yield significant advantages towards my operational implications. However, once I pass this saturation point, the improvement will sort of level off, and any improvement of my prognostic horizon and therefore my technological maturity will only yield very limited benefits. And we need to keep in mind that an improvement from a prognostic horizon from, for example, 8 flight cycle to 10 flight cycle doesn't come out of nothing. So it is associated with costs. And therefore, there's a certain saturation point where additional investment into my technological improvement doesn't really justify the subsequent improvement I'm having for my operations. So this is just a brief overview. Whoever is interested more can read here this journal publication we have placed in the International Journal of Prognostic and Health Management. There's much more background information there. Let me introduce another question that we came up and we have examined. Now we have had a look into the technological maturity, and now we wanted to understand when we're talking about legacy systems. So basically, we have a legacy fleet of A320, not equipped with any PHM technologies. And when I introduce a PHM technologies, of course, not all A320 of my legacy aircraft fleet will have the PHM technologies in an instance, but it will be rolled out successively through one aircraft to another. And we wanted to identify is there a critical fleet utilization degree that needs to be achieved in order to yield benefits for my PHM technologies. And first of all, what you can see here on the x-axis is the percentage of my proactively maintained aircraft fleet. So starting from 0% to 100%, going into 20% increments. And on the y-axis, you see my total maintenance and related expenses. Before I forget, also this has been published in Reliability Engineering System Safety. So if you want to know more further about this study, feel free to check in there. And the main observations here were, of course, also the maintenance-related expenses decrease with an increased percentage of proactively maintained aircraft. So this is rather straightforward. The more PHM systems I have within my fleet, the better I can plan my maintenance tasks, the more proactive I can plan my maintenance tasks, and my subsequent total maintenance-related expenses are likely to decrease. However, we can also see there's also a saturation point. And in this instance here, it seems like the saturation point is around 40%, which makes perfectly sense. If we're going back, I will jump back 2 slides. If we're going back to this scenario, it's not really important that I know the prediction or the failure prediction of both aircraft. So basically, I don't need to know, for example, when this aircraft is going to have their maintenance tasks happening. As long as I know the information from one aircraft, I can adapt my maintenance window in such a way that I prevent them from having this competition for the limited ground resource. So quite naturally, like a gut feeling, I would expect the saturation point to be around 50%. And because we jumped here around 40 in 20% increments, it appears to be around 40%, which coincides with the gut feeling that we are having already. And last but not least, going away from any PHM technologies, we also wanted to examine and just to demonstrate how difficult it is to have all these different stakeholder objectives aligned with one another. We wanted to examine, we're going back to the tire pressure maintenance task. We have identified, okay, tire pressure measurement has resulted in a need for a repressurization task. Now the question is, should I just repressurize the tire that has indicated it needs repressurization, or should I do it for all the tires at once on my aircraft? And here you can just get a quick glimpse of the capability of our results. So there are different KPIs that we can plot. And all these KPIs here are from an MRO perspective. So this is the cool down time. I mentioned earlier that the aircraft needs to cool down, or the tire needs to cool down after landing before I can perform maintenance. So the cool down time will be lower if I just apply my maintenance task to the individual tire rather to all tires of the aircraft. The same applies for the task execution time and the maintenance task. And if I look at these numbers from an MRO perspective, it makes totally sense. And I would come up with a solution to say, okay, I should just perform maintenance tasks in an individual tire that actually needs maintenance to have it performed. However, we're talking about a holistic approach. So basically, we're trying to extend our scope beyond just a singular stakeholder. And now we're trying to focus on the operator. And with these KPIs here, we can see that for the operator, it's quite in contrary. So the operator sees that if I perform all the aircraft maintenance, so if I perform the maintenance task in all aircraft tires simultaneously and not just on the maintenance tire, the aircraft tire that has actually the maintenance need, I can reduce my waiting time for service, I can reduce my average delay times, and I can also reduce my flight delays and flight cancellations. And therefore the operator would come up, okay, no, we pursue a different approach, and we will maintain all the aircraft tires at once and not just on an individual level. And as of this presentation, I don't have a perfect solution. So basically, it would be much more complex and complicated, and would certainly go well beyond our scope right here. But just to give you an idea that these competing interests and the competing objectives of the individual stakeholders need to be aligned, for example, through a weighting scheme. So basically putting weights on individual objectives in order to come up with a holistically improved and optimized maintenance strategy. And this concludes my presentation. If you want to know more about our institute, feel free to scan this QR code here. This will take you directly to our website. And as I mentioned earlier, we also have a LinkedIn channel where you can see some updates whenever we have some publication or anything other MRO related there. And yeah, thank you for your attention. Thank you for joining me here in the seminar. And now I'm open for any question if there are.